All right, so the plan for today is to start section 11.2 on series. I want to get this started before spring break and get a decent bit of series covered. We're a little bit ahead of schedule, but this will give us a little bit of buffer when we come back from spring break to take a little more time with some of the more challenging topics. So keep an eye out also for a supplement on some of the material from chapter 10 and from the wrap up from section 11.1. When we come back from spring break, we might, I haven't decided yet whether I'm going to include the end of section 11.2 on series as a supplemental lecture after we come back from spring break, or whether that'll just be part of the lecture when we come back. So haven't quite decided that yet, but definitely keep an eye out for those supplemental lectures for chapters 10 and 11. That material won't be due. I forget what I have the new date set at right now, but I'll go in and double check, and I'll make sure that nothing from chapter 11 is due until after spring break. So it'll be not the Sunday at the end of spring break before we come back, but the Sunday after that. I think that's April 7th. Or, well, I think I have the wrong date here from when we come back, but spring break is next week. So the quote of the day today is from Peter Arve, the co-founder of Prezi, the presentation software, that the concept of always being reachable makes us present nowhere. So I think particularly with heading into spring break, being able to disconnect for a little bit, kind of take a break from things, maybe that's a good quote for today. Okay, so moving into 11.2 series. So again, we saw a couple of times in the past, for instance, with improper integrals, that as soon as we start throwing around infinities, so to speak, we have to start being very, very careful. We have to be very cautious. We have to lay out definitions that say exactly what we mean by certain terms, and then we have to operate very strictly under those definitions. And series is probably the biggest place in the course where that really comes into play. So a series, roughly speaking, is just the sum of a sequence. We know a sequence is an infinitely long list of terms, a list of elements. If we're adding up infinitely many things, we have to be very careful about what this means, right? It's very similar in a sense to an improper integral, where we have kind of an infinitely long area that we're trying to find the area of. So again, we have to be super careful with definitions. And before we even get into series, I want to kind of throw out a disclaimer. If you look for some of this stuff on YouTube, if you look for infinite series on YouTube, probably the most popular or the most liked or most viewed or whatever videos are videos like, for instance, there's one from Numberphile, a very reputable group of folks, where they talk about, like, I think the sum, like 1 plus 2 plus 3 plus 4 plus 5 forever, like adds up to -1/12 or something. And they go through a bunch of, whatever machinations to show that. And a lot of these, surprising series results are, number one, the ones that get people to watch the video. So they're the most upvoted or the most viewed or the most liked, because they're surprising and people are like, how is that possible? But they don't operate under the same assumptions that we have here. Some of the videos are just wrong, not the Numberphile one, but a lot of them just operate under, say, maybe a slightly different definition of convergence, or they operate maybe in a different number system or something like that. And that's how they're really getting away with this. And a lot of the hand waviness is where they're not really being super careful about exactly what assumptions they're making. And they make slightly different assumptions than we make, and they get conclusions that are different than we would conclude under our assumptions. So just be very careful when when you're poking around the internet and you see crazy claims about sums of series or sums of infinite sequences or something like that that just seem off, I just advise an extra level of caution. Usually when people post information about such nerdy things as, calculus and so on, it's usually right. Usually the person who's gone through the trouble uh, to make and post such a video, it's going to be correct. But in this case, for whatever reason, there seems to be just a lot of these very surprising results kind of videos that have made it out there that are maybe some of the top ones that you'll find when you're searching for them. So take everything with just a little bit of extra grain of salt. Make sure that they're carefully outlining what they mean by certain definitions or certain words they're using, like convergence or sum or something like that. Okay, so again, a series is, roughly speaking, the sum of a sequence, the sum of infinitely many terms. And we often write a series using sigma notation, so it's a little easier to write out. This symbol here we call sigma. It's the Greek capital letter S. And it kind of stands for sum. So when I say sum I equals 1 to infinity of a sub I, that means start at the lower bound, start at a1, and then continue adding terms where we increment this index by 1 and keep going until you get to the top. Well, to infinity just means keep going forever. Or if we had a number n at the top, like a number 4 or something, then we would just go through. So if this was a 4 instead of an infinity, we would go through a4 and then be done. So that's just a little bit on notation and what we're discussing here. A super important idea in series and summations is the idea of the nth partial sum. So here we have a series, we have infinitely many terms added up, and we're just going to look at the first n terms, say for instance b1 through bn added up, which we could write as sum I equals 1 to n of bi. We'll call this the nth partial sum of the series. It's the sum of the first n terms of the series. So we could have like a first partial sum, which would just be b1. The second partial sum, b1 plus b2. The third partial sum, b1 plus b2 plus b3, and so on. We could then actually think about the sequence of partial sums where this is the first element, this is the second element, the third, and so on. So the sequence, sum I equals 1 to n, b sub I, where n goes from 1 to infinity. So this is the sequence where the first element is b1, the second element b1 plus b2, and so on. We would call this the sequence of partial sums. Okay, so let's look at some examples. So for example, this summation here, sum I equals 1 to infinity of 1 over 2 to the I, that would be 1/2, 1 over 2 to the 1, plus 1/4, 1 over 2 squared, plus 1/8, 1 over 2 cubed, and so on. That's a series, that's an infinitely long summation, while say sum I equals 1 to 5 of 1 over 2 to the I, 1/2 plus 1/4 out to 1 over 32, and then stopping. This would just be the fifth partial sum of the sequence. This would be, or sorry, the fifth partial sum of the series, the fifth entry in the sequence of partial sums. And we can see the sequence of partial sums would be the first element is 1/2. The second element, 1/2 plus 1/4, or 3/4. The third element, 1/2 plus 1/4 plus 1/8. or 7/8, and so on. That would be the sequence of partial sums for this series up here. Okay, so moving on to our definition, and I put a couple of stars here because this is a very important definition. This provides the basis of really what we're going to talk about through most of chapter 11, convergence of a series. And this is where, you know, maybe a physicist operating in some certain context might want to use a slightly different definition of convergence of a series. They might use one that's quite similar to this one, but maybe with a little detail different here or there that makes some things work out a little nicer. They might use a definition that's quite different than this one, and, you know, kind of strange things like quantum mechanics or something. Maybe a definition that is very different than this one and leads to very different conclusions, like the 1 + 2, etc., equals -1/12 thing. Maybe that's a very different context. But this is the definition that we're going to be working under. And of course, the context being the typical kind of algebraic structure that we've worked through algebra and calculus to this point. So what is the definition of convergence of a series? So given a series, sum I equals 1 to infinity of a sub I, let's let big S sub n denote the nth partial sum. That is, big S sub n is sum I equals 1 to n of a sub I. And let me zoom this in just a little bit here. So given a series, denote its nth partial sum by S sub n. This generates a sequence of partial sums, S1, S2, S3, and so on. The sequence of partial sums, sequence Sn. If the sequence of partial sums, Sn, is convergent, in other words, if Sn goes to S, a real number, then we say the series converges. We say the series is convergent. So we define convergence of a series by looking at the sequence of partial sums and evaluating whether that sequence of partial sums converges. In other words, up here, as I tack more and more and more terms on, does the summation kind of settle down to a limit? Does it maybe grow without bound, go to plus or minus infinity? Does it maybe just keep bouncing around and never really settle down? If it settles down to a limit, then the series converges. If it keeps bouncing around or shoots off to an infinity or something, then the series does not converge, the series diverges. So if the sequence of partial sums is convergent, then we say the series is convergent. And furthermore, convergent series have a sum. Furthermore, we say that S, the real number that the sequence of partial sums converges to, we say that S is the sum of the series, and we write the series equals S. Sum I equals 1 to infinity, AI equals S. And this is precisely what we mean when we write a notation like this. We mean that we have constructed, or at least could construct, the nth partial sum. Think of the series of, or sorry, think of the sequence of partial sums, and know that that sequence converges to S, which is the sum of the series. Okay, so let's take a look at our previous series, 2 to the minus powers, and let's see what we think. It kind of seems like, if we look at our partial sums up here, it kind of seems like these are headed to 1. Does it seem plausible that this is true? Can we prove it carefully? Let's start with the plausibility argument. And the plausibility argument is one that I think I've even mentioned before in this class, but it's a somewhat, I guess, famous one. Suppose we have a say like a pizza, something that's a circle that's its unit area. And we have infinitely many people to feed. So we say, okay, each person, line up, each person, when you get up, when it's your turn to take your slice of pizza, you can take half of what's left. So the first person gets lucky, they get half of a pizza. The second person gets a quarter pizza. So the first person took a half, leaving a half. The second person takes half of what's left, or half of a half, a quarter, leaving 1/8, or sorry, leaving 1/4. The next person takes half of what's left, 1/8, leaving 1/8. Next person takes 1/16, leaving 1/16, and so on. And we can see that if we just keep chipping away, cutting each of the remaining slices in half and doing that over and over and over, we should eventually use up the whole pizza. It'll take infinitely long, but we're certainly working our way towards that. So it seems plausible that there should be one. Can we prove it carefully? Well, I'll leave as an exercise, but we can see that Sn is going to be 1 minus 1/2 to the n. So this is like 1/2 is 1 minus 1/2 to the 1. 3/4 is 1 minus 1/2 to the second. 7/8, 7/8, 1 minus 1/2 cubed, and so on. And we can see that as n goes to infinity, this does indeed go to 1. The sequence of partial sums, that sequence has limit 1. And now we can confidently come back up here and say that this series is equal to 1. Okay, let's look at a theorem. This is a helpful theorem for evaluating convergence or divergence of a series. And this theorem is a test for divergence. And the theorem says the following. It says, if a sub I does not go to 0, then the series, sum I equals 1 to infinity, a sub I diverges. It does not converge. Now, a couple notes here. We can't use this the other way. We can't say that what this theorem does not say is that if AI goes to 0, then the series converges. The theorem does not say that, and in general, that is not true. If the terms get smaller and smaller in magnitude, the series might or might not converge. But certainly, if the terms do not get smaller and smaller in magnitude, then the series must diverge. We have to be a little careful here because we're dealing with two ideas. We're dealing with this kind of sequence of AIs. But the convergence or divergence of the series is interested in the sequence of partial sums. Oops, I equals 1 to infinity. I know I'm scribbling a little bit here, but I'm trying to write quickly because I think we know kind of what I'm writing. We have the sequence of AIs, first element A1, second element A2, third element A3, and so on. We have the sequence of partial sums, SNs, n equals 1 to infinity, which is S1 is the first element, S2 is the second element, and so on. S1 is the sum of the first one element of the AI sequence, so that's just A1. S2, the sum of the first two elements, A1 plus A2. S3, A1 plus A2 plus A3, and so on. We have two different sequences we're working with here, both of which are related to this series in some way. Our question is, does the AI sequence go to 0? If not, then we're saying that this sequence of partial sums does not go to a limit that's a real number. Something we're going to lean on heavily here is the contrapositive. So just a reminder, a lot of our theorems look like if A, then B, or A implies B. As a general rule, if we have this theorem, if we constructed another statement, if not A, then not B, that would not necessarily follow, right? So if we tried to make the argument that because this statement holds, it's a theorem, we're going to prove it in a second, then if not A, if AI does not go to 0, if AI goes to 0, then some AI does not diverge. If we tried to make that statement that if AI goes to 0, then some AI converges, that's generally not true. However, we can make a statement related to the just lost the word, to the negations of these two criteria, A and B. And that's the following. If not B, then not A. Or not B implies not A. And I think we can just kind of understand this logically, right? If A is true, then B has to be true. If B is not true, then A cannot be true, right? If B was not true, but A was true, well, if B was not true and A was true, what does that say about this statement? B is not true, but A is true. But this statement says anytime that A is true, B has to be true. So B has to be what? Not true and true at the same time. We don't allow for that in propositional logic. So this isn't, some kind of Schrodinger's cat kind of a deal or something. So these two statements have the same truth value. They're equivalent statements. They're logically equivalent statements. So this is the theorem I want to prove. If the elements of the sequence that the series is constructed from, if the AIs do not go to 0, then the series diverges, then some AI diverges. The contrapositive has the same truth value. And it would say if some AI does not diverge, in other words, if some AI converges, then AI does not go to 0, or AI must go to 0. So we negate the two and we flip them. That's the contrapositive. That has the same truth value as the original statement. So we'll prove the contrapositive, we'll prove this direction, and then that will imply the original test for divergence. Okay, so under the contrapositive, our assumption is that the series converges. That means that the series is equal to the limit of the sequence of partial sums, and that limit is, I'll call it L here, which is a real number. But if I take a sequence and I re-index it, that doesn't change its limit. If I just, call this whatever S2 and this S3 and the next one S4 instead of 1, 2, 3, that doesn't change the value of that, or that doesn't change the limit. So coming down here now, limit n goes to infinity of Sn has to equal limit n goes to infinity of Sn minus 1. Still has to be L, a real number. So on one hand, we have L equals limit n goes to infinity Sn, but we can construct Sn, the nth partial sum, as the n minus first partial sum plus the nth term in the series. So Sn is Sn minus 1 plus An. The limit of the sums is the sum of the limits. And we know that limit n goes to infinity Sn minus 1 is L. So what do I have? I have that L equals L plus something. Well, I subtract L off of both sides, and I get limit n goes to infinity of An equals 0, which is what we wanted to prove. If the series converges, then the terms go to 0. And then that also proves the test for divergence, that if the terms don't go to 0, the series must diverge. So let's look at a couple examples. Let's look back at our series sum of 1 over 2 to the I. We know that this converges. And that implies through our corollary that 1 over 2 to the I goes to 0. Not a big surprise there. We didn't really learn a whole lot from this statement, but just using that corollary, just showing how it could be used. The next example we might not know the answer to right away, though. If I look at the series, sum I equals 1 to infinity of 1 plus I over 1 plus 2I, what do we think about this series? Do we think this series is going to converge or diverge? It might not be clear at first, but we realize that the individual terms, 1 plus I over 1 plus 2I, as I goes to infinity, this goes to 1/2, right? The 1 pluses, their contribution becomes negligible, and we just end up going to 1/2, or we could go through and divide top and bottom by I and work through it formally that way, but we see this just goes to 1/2. But 1/2, the limit of the sequence of the terms, this is not 0. So my individual terms limit to a real number, but not 0. Therefore, my series must diverge by the test for divergence. We have to be extra careful, as I mentioned before, because we're talking about convergence of a sequence and convergence of a series kind of at the same time here, but they're different ideas, right? Convergence of a sequence, convergence of the sequence of the terms of the series is what we're looking at in the test for divergence. Convergence of the sequence of partial sums is what we're looking at as far as convergence of the series, or whether that series has a sum, or what the sum is if it does have a sum. So again, there are a lot of details here. There's a good bit of semantics, just a lot of words that we're using. I'm trying to use them very carefully. I probably will slip up once or twice, but I'm trying to be very careful when I talk about convergence of a sequence or a series, or convergence of the sequence of partial sums, or convergence of the sequence of the terms of the series, trying to be careful with all of my vocabulary and making sure that I use it precisely. Again, these are different ideas. They're operating side by side when we're talking about series and convergence of a series. And again, super important to realize the test for divergence says if the individual terms of a series do not go to zero, the series diverges. If the individual terms do go to zero, then the series may or may not diverge and may or may not converge. If the antecedent is not satisfied, we can't say anything about the consequent. Okay, let's take a look at the geometric series then. So we're going to look at the series sum I equals 0 to infinity of r to the I, where r is some real number. So r to the 0 is 1 plus r squared plus r cubed, and so on. In the previous lecture, we looked at the sequence where the elements were r to the I. So we looked at the sequence like r squared, r cubed, and so on, and we did some work with that. Let's look at this series and decide for what values of r do we think the series is convergent. Well, I think it should be convergent for maybe you say r equals 0, right? If r was 0, what are my partial sums? Well, it's like 1 plus 0, 1 plus 0 plus 0, 1 plus, right? My sequence of partial sums is just 1 forever. That goes to 1. If I have an r like 2, this should not be convergent. This series should diverge. Why is that? Well, if I look at, now I'm going to be careful. Let's call these a sub I, the individual terms a sub I. If I look at the sequence of individual terms, what does that look like? 2 to the 0 is 1. 2 to the 1 is 2. 4, 8, 16, so on. This goes to infinity is not a real number. By the test for divergence, by the divergence criterion, because my individual terms do not go to 0, I said not a real number, but I should have said not 0. Because my individual terms do not go to 0, then my series must diverge. What if I consider something like r equals -1? Not quite sure. Let's take a look at that. What would my sequence of partial sums be? Well, -1 to the 0 is 1. -1 to the 0 plus -1 to the 1 is 1 minus 1. That's 0. And then I add 1, and then 0, and then 1, and then 0. This just bounces around. What's the limit of this? The limit doesn't exist. The limit of the sequence of partial sums doesn't exist. So this should diverge. Okay, I have a little bit of an idea of what some of the behaviors are for different r's. But can I get an answer more generally? Well, let's look at the nth partial sum. The nth partial sum is 1 plus r squared, and so on, out to r to the n. Okay, so what could I do here? There's kind of a somewhat famous trick. If I take r times the sequence of partial sums. Now, as an aside, when I'm dealing with the series, when I'm dealing with an infinitely long summation. I can't just go throwing around algebraic properties willy-nilly. I have to be very, very careful. But here, note, I'm in the partial sum. I have a finite number of terms. All of my normal algebraic properties work just fine here. This is just n+1 things added together. I can do things like commutative property and associative property and multiplying and all kinds of good stuff here. No problem here. All right, so r times Sn, that would be r times 1, or that's r times r, or r squared, all the way out to r times n minus 1 is r to the n, and r times r to the n is r to the power n plus 1. I see that I can match up most of the terms. If I put a, OneNote doesn't want me to put a minus sign there, it's putting this crazy arrow in the way. But if I put a minus in front of there, and I subtract the two, again, why can I subtract these? I'm not subtracting infinite series, I'm subtracting partial sums. This is just the sum of n plus 1 terms. So minus r times Sn just makes each of these a minus. And if I add these together, 1 minus r Sn equals, again, why can I add them together or do any of this? I'm in the partial sum, super important detail. I don't want to go doing this kind of stuff inside a series. I notice that all of the stuff in the middle goes away. And on the right side, I get 1 minus r to the n plus 1. Or a formula for my nth partial sum is 1 minus r to the n plus 1 over 1 minus r. Now, one little caveat is this is when r is not equal to 1. Otherwise, we just have 0 equals 0. And then we can't divide through. So let's just knock out that special case. What about when r equals 1? What are my AIs? R to the 0 is 1, r to the 1 is 1, r to the 2 is 1. My AIs, my sequence of the individual terms, goes to 1, which is not 0. So we diverge at r equals 1. Now that that special case is out of the way, let's look at what happens to our sequence of partial sums. As n goes to infinity for a specific choice of r, what happens to Sn? Or what happens to 1 minus r to the n plus 1 over 1 minus r as n goes to infinity? Well, note that 1 minus r in the denominator isn't actually doing anything. The 1 in the numerator isn't actually doing anything. It's not changing as n goes to infinity. So really the question is, what does r to the n plus 1 go to as n goes to infinity? Or really, this is just a question about the convergence of the sequence, r to the n, right? And what do we say? We said this converges if and only if r is in -1 to 1. We did include positive 1 when just discussing the sequence. But here we've kind of excluded consideration of r equals 1. So I'm going to come down here and say that r to the n plus 1 or r to the n converges if and only if r is strictly between -1 and 1. Or in other words, the sequence of partial sums converges if and only if r is strictly between -1 and 1. We know it doesn't converge at 1. We handled that special case up here. So r has to be strictly between -1 and 1. And we can even say a little more. We can actually say in this case, well, r to the n or r to the n plus 1 converges to 0. So this bit goes to 0. So Sn actually converges to 1 over 1 minus r. If and only if r is between -1 and 1. And this meshes with what we found up here. We said, yes, no, no, no. That meshes with the criterion that we found below. So we can say that this series equals 1 over 1 minus r if, well, let me say if r is strictly between -1 and 1 and diverges otherwise. So we can say for what r's the series converges, and we can even say what its value is, what its sum is, in the instances it does converge. Now there are some components of the, or some choices for r, let's say, where we might say they diverge, but you know, some folks in the applied fields would look at something like this and say, okay, that like really diverges. We're just adding bigger and bigger and bigger terms each time. But this, like, maybe they would look at this and they would say, well, I mean, it kind of stays around the same number. Could we call like the sum 1/2 or something? That's something you'll see a lot in physics, where it's some kind of like long run average of the sequence of partial sums. Again, different people in different contexts working under slightly different definitions or very different definitions might make different statements, might make different conclusions here. Particularly this one is one that you see often in some of the applied fields. But we're working very strictly under our definitions, under our context. And under our definition, this r equals -1 does not converge. So a word of warning with trying to do algebra or arithmetic under series when we have an infinite sum. So let's look at this, proof, so to speak, that 0 equals 1. I don't know why my 1 won't line up with the rest of them. There we go. So let's look at this, supposed proof that 0 equals 1. So we start with 0. Pretty clearly, 0 is the sum of the series where all of the elements are just 0. I don't think there's any question about that, right? The first partial sum would be 0. The second partial sum, second partial sum will be 0. The third partial sum will be 0, and so on. So 0 is pretty clearly the sum for the series where all of the elements are 0. We could take each of these terms of the series, each of these zeros, and choose to write it as 1 minus 1 instead. There's the second 0. There's the third 0. We could write 0 as 1 minus 1, no problem with that, seemingly. We can use the associative property and just reorder how we're adding together the 1s and minus 1s. We're going on forever, so there's always going to be a next +1 to match up with my previous -1. So I can just kind of shift my parentheses all down to the right one term. But now I have a little bit of a problem. If I use the same idea that I did here, I can do -1 plus 1 is 0. The next -1 plus 1 is 0, and so on. But this is pretty clearly 1 plus a series, which is all zeros, 1 plus this original series, or 1 plus 0, but that's just 1. Where did I go wrong here? All the things I did seem plausible. Let's take a more careful look. Let's try to do this, but let's try to do it in terms of the partial sum instead of the series. So 0, maybe I'll write it this way, is the limit of the sum I equals 0 to infinity of 0, or I equals 1 to infinity of 0. Let me rewrite that. It's messy. So we're looking at sum I equals 1 to infinity of 0. So 0 is clearly the limit of the sequence of partial sums. But the nth partial sum is 0 plus 0 plus 0 plus 0 n times. What was my next step? I turned the zeros into 1 minus 1s. Plus 1 minus 1. And parentheses. Now I'm going to use my associative property. There's those two plus -1 plus 1. There's the next two plus -1 plus 1. And then I'm left with a -1 at the end. Or this is 1 plus a whole bunch of zeros, -1, or 1 minus 1 is 0. And now we don't get any problem, right? What did I do here? Well, I used my associative property when I really ought not have. Right, just counting on this ability to always get another +1 to balance out the -1. That was something that I'm not sure if I can use that in infinite series. I don't have a theorem or a property that says, yes, you can use associative property in infinite series like this. Again, I have to be very careful about the assumptions I make. Can I do that in the sequence of partial sums? Yeah, no problem at all, because this is just a finite sum. It works the same way that our algebra has always worked. But in the infinite series, again, we have to be super careful. Okay, so let's look at this series. Sum I equals 1 to infinity of 2 over 4i squared minus 1. So we want to do some algebraic manipulation of this, but again, we want to be very careful, not do that algebraic manipulation in the series. We want to do it in the partial sum. So let's consider Sn. Sn equals sum I equals 1 to n of 2 over 4i squared minus 1. Now that I'm in my sequence of partial sums, I can do all the algebra that I want. I don't have to worry about any of that, any of this kind of nonsense up here. I can rearrange things. I can use associative commutative properties, all of that kind of stuff. No problem. I'm going to use a partial fractions kind of idea here. I notice that the denominator is 2i minus 1 times 2i plus 1. I know I want my two i's to go away. So if I do something like this, I get a 2i plus 1 minus a 2i minus 1. So the 2i minus 2i goes away, and a plus 1 minus the negative 1 becomes a 2. That looks good. So I made this a pretty easy partial fractions problem. If it was more complicated, we'd have to go through that, find the a and b and all that. But what do I notice here? My I equals 1 term has 1 over 2 minus 1 minus 1 over 2 plus 1, or 1 over 1 minus 1 over 3, plus my I equals 2 term, 1 over 4 minus 1 minus 1 over 4 plus 1, or 1 over 3 minus 1 over 5. My I equals 3 term will go one more. So 1 over 6 minus 1 minus 1 over 6 plus 1. So it's plus 1/5 minus 1/7. And what we might see is that I can now rearrange how I add these together, right? This is called a telescoping series. But all importantly, we don't just say, okay, and this happens forever. We have to say, what's my n minus first term? So what's that? 1 over 2n minus 2 minus 1 is minus 3, minus 1 over 2n minus 1. And then my I equals n term, 1 over 2n minus 1 minus 1 over 2n plus 1. So these two just get appended on at the bottom as well. So now I can go through, and I'm going to try to just use my eraser to do this so it's a little quicker. But I'm just going to rearrange my terms. Why can I do this? Again, very importantly, because I'm in the partial sum. I'm not doing this in the series. I'm doing this in the partial sum. So this is going to be plus a negative 1/3 plus a third, plus a negative 1/5 plus a fifth, plus a negative 1/7 plus a seventh, and so on. I'm going to have plus a negative 1 over 2n minus 3 plus that, plus a negative 1 over 2n minus 1 plus a 1 over 2n minus 1, and then minus this extra term at the end. I notice that each of these parentheses in the middle here are going to cancel out. So it's a telescoping sum because the partial sums, the middle terms all collapse, and I end up just getting that Sn equals 1 minus 1 over 2n plus 1. I have a nice simple formula for Sn. This doesn't often happen. I mean, it worked nicely for the geometric series. It works nicely for this telescoping series. It doesn't often happen, though, that Sn turns out to be a really nice function of n. But in this case, we do get a nice function, and we see that Sn goes to, as n goes to infinity, 1 minus 0, or just 1. We see that this series converges, and its sum is 1. So we were able to use some algebra and some manipulation, again, extremely importantly, inside of the partial sum, not inside of the series. And then we were able to cancel a bunch of stuff out and show that the sequence of partial sums goes to one. Therefore, the series converges and its sum is one. Now, had we gotten something similar where a bunch of stuff canceled out of the middle, but this was like, let's say we ended up with, instead of this, if we ended up with 1 minus n squared or something, well, this does not go to a real valued limit. So then our series would not converge. We could have a series that results in a telescoping partial sum where we can write the formula for the nth partial sum really nicely, but the whole thing diverges, right? So we had to be careful, and we had to go through this last step of verifying that not only does everything telescope nicely and all that, we still had this extra kind of vestigial term at the end here. We did include that, and we did show that that sequence of partial sums converges to one. Okay. I think we will leave the next example in this discussion on harmonic series either for the supplement or for when we come back next time. I'm kind of leaning toward just covering this, at least these two topics when we come back next time after break, just to kind of get us back in the swing of things. So again, keep an eye out for supplements that I'll post coming up here. I'll stop the recording.